We're now going to look at some very important reactions called the aldol reactions. One of the things that can be confusing about the aldol reactions is that there are actually two aldol reactions. There's one that most properly should be called the aldol addition, and then there's one that should be called the aldol condensation. We're going to separate these reactions and discuss each individually, but it is often the case in some textbooks that the authors are not careful to distinguish between the two different reactions, and in fact, very often use the term aldol condensation for both. The aldol addition, sometimes called the aldol reaction, looks like this. In the aldol addition, we actually have two molecules of the same aldehyde or ketone. One of the molecules is going to act like a donor, and one of them is going to act like an acceptor. The alpha carbon of the donor becomes connected to the C+ carbonyl carbon of the acceptor. Now, when that carbon attaches to C+, that's a nucleophilic addition. We have to push the pair of electrons out of the way on the carbonyl, and we end up with an alcohol OH after protonation. So you can see that the product is a molecule that is composed in part from the donor and in part from the acceptor. Now, this product historically is mostly made using aldehydes, and the product would therefore be an aldehyde alcohol, technically a beta hydroxyaldehyde. So therefore, it was given the name aldehyde alcohol, aldol. One confusing thing about this reaction is that often, instead of writing a molecule of the donor and a molecule of the acceptor, just one molecule will be written, since the donor and the acceptor are technically the same molecules. In that case, then, you would only have one of these written, you would have the conditions, and you would be expected to assume that even though only one molecule is written, we have two molecules reacting. In the aldol condensation, we also have an aldehyde or ketone donor and an aldehyde or ketone acceptor. We're also going to form a bond from the alpha carbon of the donor to the carbon plus of the acceptor. We're going to use NaOH as we used in the aldol. However, we are going to add heat. We're going to heat the reaction. In that case, the reaction does additional things after the aldol is formed. And specifically, there is an elimination that occurs between the alpha carbon and the C+ carbon, forming a double bond and removing a molecule of water. The product, therefore, is not an aldol anymore, since there is no alcohol. Instead, it is called an alpha-beta unsaturated aldehyde or ketone. If this is our aldehyde, here's alpha, and although we've labeled this C+ to show the reactivity from the acceptor, technically this is in the beta position along the chain. This is called a condensation. In a condensation reaction, the reactants come together to form a product, but the formula of the product has a small molecule removed. So in this case, the small molecule is water, which is a very common small molecule to have removed. We're now going to look at the mechanism of both the aldol addition and the aldol condensation. The mechanism starts with the donor aldehyde or ketone. We get acid-base reaction using a base, removing a hydrogen from the alpha carbon of the donor, and forming an enolate. The enolate in this form, if we look at it, it has a carbon minus on the alpha carbon with a lone pair. That carbon minus can act as a nucleophile, similar to the way a Grignard reagent acted as a nucleophile. So the lone pair can approach the C double bond O carbon and make a bond. However, in order to be able to form that bond and not form 5 bonds to that carbon, we need to push a pair of electrons out of the way from the C double bond O onto the oxygen. So we get this intermediate. we have a new bond formed between alpha and carbon plus, and we have an O- oxygen. That can become stabilized by deprotonating some acid in the system, very often the conjugate acid of our original base, and that creates our aldol. This is where the aldol addition stops. However, it should be pointed out that every step in this first part of the mechanism is reversible. If a base deprotonates the aldol, we get this intermediate. This intermediate has a tetrahedral intermediate right here. There's electron pressure. If it pushed down, it could push out the enolate, and we would go backwards to our reactant. That process is called a retroaldol reaction, and we're going to see that when we look at biochemistry. There's a very important reaction in one of the biochemical pathways that involves a retro or reverse aldol reaction. The aldol condensation continues from the initial aldol product. In the aldol condensation, a base deprotonates the alpha carbon again. That creates an enolate where we have, again, a lone pair on the alpha carbon adjacent to the aldehyde or ketone carbonyl. In this case, that lone pair pushes down toward the OH group, OH being an acceptable leaving group, and it pushes the OH out. This forms a double bond between alpha and carbon plus, and this is the product of our aldol condensation. While the first deprotonation following formation of the aldol is reversible, the second elimination reaction step is not. To summarize the features of the aldol mechanism, two carbonyl molecules react. One will be the electron donor. It will be the molecule that forms the enolate. The other molecule will be the electron acceptor. It will accept electrons of a nucleophile at the carbonyl carbon, carbon plus. There will be a new bond formed between the alpha carbon of the donor and the carbon plus carbon of the acceptor. And the reaction steps are reversible up until the step that forms the double bond in the condensation. The equilibrium for the aldol reaction, stopping at the aldol, is disfavored for ketones. Ketones will almost always prefer to be separated ketones. They will almost always go backwards because of the steric hindrance in the aldol reaction product. Therefore, ketones must almost always be dehydrated using an aldol condensation, or no products will be isolated. The aldol reactions that we've discussed up until now have two identical reactants. While very useful, that does limit the products that we can form. It would be much more versatile if we could use two different molecules, one as a donor, one as an acceptor. This would be called a crossed aldol reaction, an aldol reaction in which the two carbonyl compounds are not identical. We're going to look at the crossed aldol reaction using a condensation because ketones will generally not form aldol products. Instead, they will stay mostly unreacted. So what we're going to do is look at having a donor and an acceptor, and the donor and the acceptor are going to have two hydrogens on the alpha carbon and then some carbon group attached here. If the carbon groups are not identical, then these would be two different structures. If we look, we have several different possible combinations of these two molecules in our products. Because they are mixed together, they're treated with base, and therefore, in theory, either one could actually become deprotonated and be the donor. So we're looking at having a desired donor and a desired acceptor, but we may not be able to control that once they are mixed together. So if we were to look at our desired product, it would look like this. Donor alpha, acceptor carbon plus. However, there are three other possible undesired products. For example, what if the acceptor instead became deprotonated and acted like a donor, we would get a product that would look like this: acceptor attached to donor, the reverse of the structure that we want. Furthermore, once the donor is deprotonated, if it's not completely deprotonated, if there are unreacted donor molecules, they can actually be acceptors, so we could get donor attached to donor. And similarly, if the acceptor were deprotonated, we could get acceptor attached to acceptor. Therefore, we get a mixture in a typical simple crossed aldol reaction of 4 different products, only one of which would be our desired product. Now, if the donor and the acceptor are identical, can you see then that these would all be identical products? So that would be very practical. But getting 4 different products means we're throwing away up to 75% or more of our reactants, only getting 25%, something like that, of our desired products. However, it is possible to do a crossed aldol when the acceptor has no alpha hydrogens. In that case, then, the acceptor cannot be deprotonated on the alpha carbon, so it will never act as a donor. That means that the products where the acceptor has attached to the donor or the acceptor has attached to the acceptor cannot be formed, which is going to make this a much more efficient reaction. Here's an example. We have this aldehyde, acid aldehyde, which has a CH3 in the alpha position, has alpha carbons that can be deprotonated. This aldehyde, benzaldehyde, has no alpha hydrogens, because if we look, this carbon already has 4 bonds. So in this line structure, there are no assumed hydrogens at this alpha position. Therefore, if we deprotonate the donor, we have a good chance of having it react preferentially with our desired acceptor. Again, using heat to dehydrate the aldol product, we would get the aldol condensation product, which would look like this. We can extend this by using a ketone as the carbonyl donor, using an aldehyde acceptor that has no alpha hydrogen. In classical O-Chem, this was called the Claisen-Schmidt reaction, although in reality, it's just a modified crossed aldol. So here's an example. Here we have a donor ketone. This ketone was selected so that only one of the alpha carbons has hydrogens, so that we don't have to worry about kinetic versus thermodynamic. Here again is our benzaldehyde aldehyde acceptor, which can't be deprotonated in the alpha position. The ketone will become deprotonated, it will attach to carbon plus, it will be dehydrated, and we will get this product. When a compound contains 2 carbonyls in the same molecule, treatment with base can form a ring. Again, this is most commonly done as a condensation. Here's an example. This is a 1, 2, 3, 4, 5, 6, 7 carbon dialdehyde. I've numbered starting from the alpha carbon of one of the aldehydes to carbon plus of the other aldehyde to show how many carbons would be in a ring that would be formed if we attached the alpha carbon to carbon plus from here to there. This would form a 6-membered ring like this. If we dehydrated between alpha and carbon plus, the new bond that was formed, which would be right here, we would get a double bond there in the ring. And because of the way this is set up, the aldehyde carbon would be outside attached to the ring. Because this reaction forms a ring, we call this the aldol cyclization. It's an intramolecular aldol condensation that forms a ring. If we use a ketone as our donor, the ketone can have the possibility of having 2 alpha carbons. In this case, I've labeled them as alpha and alpha prime. In that case, then, the alpha carbons would form rings of different sizes. For example, if we start counting on alpha 1, we can see that it would be 1, 2, 3, 4, 5, 6 carbons. That would form a 6-membered ring. If we start counting on alpha prime, we can see that we would form a 1, 2, 3, 4 carbon ring. In general, what we see is that 5 or 6-membered rings are preferred instead of 3 or 4 or 7-membered rings, because 5 and 6-membered rings have the smallest amount of ring strain, which means that it takes the least amount of potential energy to form them. So in this case, alpha would react preferentially, and we would get this 6-membered ring product instead of this 4-membered ring product. When the compound contains an aldehyde and a ketone, the ketone will form the enolate and the aldehyde will be the acceptor. So again, if we look at this one, we can see that we have two different alphas. In this particular case, the alpha here will form a 5-membered ring, whereas the alpha prime would form a 7-membered ring. So alpha would be the preferred alpha reactant, and we would get this product.